So, welcome back to the course on architectural design of ICs. So, in the last class we are seeing that fixed point number representation. That means, whenever we are implementing any system or any function or any algorithm in hardware. So, at that time we have to do it in fixed point domain. So, for that we have to convert from floating point to the fixed point. Because of the conversion, there is some error we basically gathers or we accumulate. Okay. So, depending on the error, the performance of the system that may be degraded. Okay. So, for the degradation of the performance, what is the effect? So, we will take one example of any filter design, and then we will see how basically doing this or for this conversion of floating point to fixed point, how basically it affects the performance of the corresponding system design. So, that we will see in today's class. Okay. So, suppose we have to what I said in the last class, that whenever we are doing this filter implementation. So, at that time we have to, that means we have to bother about the corresponding conversion in two area. That means, one is for the coefficient, another for the arithmetic operation whatever we are doing for filter implementation. Okay. So, that means, for the coefficient quantization, the quantization of the coefficient that may be creates the problem. Okay. Suppose in MATLAB, if I take the corresponding, what I said, that the corresponding coefficient values, they are basically in the fractional domain as the maximum value that may not be greater than 1. So, that means, all the coefficient values, they are represented in fractional bits only. Okay. So, what will be the exact value, or sorry, what will be the exact word length to represent each of these coefficient, that is basically very much critical. Okay. So, if I just consider that the filter coefficient that may be represented, if it is represented using 15 decimal digit or 15 bits, then this corresponding filter specification that it satisfy or that basically meets the specification. Okay. For implementation, this we need to quantize the coefficient to the word length used for the implementation. Okay. So, for this quantization of this coefficient, what will be the, that means minimum number of this, that means the word length of the coefficient to meet the proper constraint on the specification of the filters, that we have to analyze using, or that we can analyze using MATLAB. Okay. So, in the present day digital signal processor, this has become say less of a problem, because this 16 bits equals to 4 decimal digits or 24 bits, that is equals to say 7 decimal digit precision. In hardware design with the tight speed requirement, this is still a relevant problem for this. What is basically meaning is that, what will be the that means corresponding. So, 15 decimal digit means it is basically to the word length for that is basically 60 bit. Okay. So, to 60 bit means in the multiple constant, actually we have taken the example of FIR filter at the time. So, we need the multiple constant where we have to consider the multiplier bit length of 60 bit. Okay. So, to meet the corresponding specification. So, 60 bit means it requires a lot of hardware, right. So, to reduce that, what will be the, that means the optimum word length that we will see. Suppose we have, that means this, okay, not this one. Suppose we have to implement one FIR filter which has the specification of passband attenuation of 0.01 with the radial frequency of 0 to 0.4 pi and the stop band attenuation of 0.001 with radial frequency of 0.4 pi to pi. Okay. So, if you just see this is the, that means the corresponding the filter response. Okay. This is a filter response and this is the this pole 0 plot, this is the pole 0 plot, okay, considering the unquantized coefficient. That means, where each of this pole and 0, that means each of the coefficient has been considered in a on its original value. Original value means if the value is, let us say if the value is, that means 0.0000000001 to something like this. So, any of this value, if this is the real value of this coefficient, if I consider, then this is the corresponding, that means pole 0 location which I am getting. This is the actual pole 0 location of this particular FIR filter. Okay. Now, the thing is that, okay, if I take fixed point coefficient, so at that time what will happen? Okay. So, if the FIR filter consider the coefficients of 16 bits, so at that time the corresponding pole 0 location will be something like this. Okay. So, how it is different? It is not that much different from the this unquantized coefficient one. That means, it is more likely, or if you just see, it is more likely closer to the this unquantized one. The performance of this is not degraded if I consider the coefficients are of each of 16 bits. Okay. But if you just consider that, if you just consider this coefficients of 8 bits, so at that time you see these are basically deviating. So, that means, if this is the original one, okay, if this is the original one, then this is the corresponding to the, considering the fact that each of the coefficients are of 16 bit. But if I consider each of 8 bit, so at that time this basically this 0 location, they are basically deviating from the original one. So, that means the performance and it is actually, it is sometimes it is basically going beyond of this unity circle. Okay. So, that means your filter whatever you have implemented in hardware, that may be unstable at that time. So, it is not, that means permissible, or it is not advisable that whatever hardware I have designed, the filter hardware if I have designed considering the fact that each of the coefficients are of 8 bits. So, at that time the filter response may be, or the performance of the filter, that may be unstable at that time. So, in some of the case it may be unstable. Okay. So, that is not desirable. So, to avoid that, we need to do this, what will be the, that means corresponding this word length for this. So, that we have to consider. Okay. So, what is the benefit here? That means, for if I consider each of the bits, each of the coefficients are of 8 bit, that means the hardware for doing this that constant multiplication, that will be less at that time. If I consider 16 bits, so at that time I need more number of adder to do that multiple constant, but if I consider 8 bits, so at that time I need lesser number of adder to that means to implement that. But I have to keep in mind that my performance is degraded, that is not at all satisfying the overall whatever is my desired, that means specification or desired functionality of the filter. If that is not meeting, so at that time this is not the case which I will consider. Okay. So, this is the fact which we have to keep, that means analyze from the beginning, that means from the implementation of the hardware itself. Okay. So, then that means the quantization that may happen or that is required for the arithmetic operation 2. So, in the arithmetic operation 2 for the addition operation, what I need, if two bit numbers are added, then the results has to be of b plus 1 number of bits. Okay. And then for the constant multiplication, if a b1 bit number is multiplied by a b2 number of bit, so at that time the result has to be of b1 plus b2 minus 1 number of bits. Okay. So, that means for the multiplication the word length will be b1 plus b2 minus 1. For this addition, that minimum requirement of that corresponding to hold the proper result, that means to reduce the overflow or to avoid the overflow, we need to consider the corresponding bits for the addition b plus 1, for multiplication that is b1 plus b2 minus 1. Okay. Then for typically, or for this is for IR filter, or sorry, FIR filter, for especially for IR filter, the results of an addition or multiplication has to be represented again as a b number of bits. Hence, to get rid of either most significant bits or less significant bits. Means what? When in IR filter, when there is feedback, so that means for this arithmetic operation, whatever error I will gather, so that will be run in a loop. Okay. So, run in a loop means as that particular point is basically affecting the overall performance of the filter. So, at that time I have to be consider this fact, or I have to be more cautious while considering this corresponding word length for this multiplication as well as this addition operation. Okay. For the FIR filter, if it not that much, if it not that much it affects, but for IR filter representation or IR filter design, this arithmetic operation truncation or the corresponding word length selection of the arithmetic operation, that basically means affects a lot. Okay. So, in arithmetic operation, so we can have two options, one is this for MSB, another one is for LSB. Okay. LSB, when I require, basically if I miss the MSB, that means I can, what I said, that if I suppose to hold the data or hold the result, if I represent that okay, I need only 9 bit, that means if the result is more than 511, so at that time the result will be represented for 512, the result will be 0, though the result is 512 at that time. That means there will be one overflow if I miss the MSB, and if I miss the LSB, that means there will be the truncation or this quantization error. Okay. So, that means quantization error means suppose I am having this, suppose I am having 3, if the last bit if I just missed, so that means the data will now become 1. So, that means 2 is the error which I am basically accommodating for just missing one of the LSB. Okay. So, that means in both the case, for considering the fact of LSB and considering the fact of missing the MSB, in both the case for MSB I am doing, or I am just doing this overflow, I am getting overflow, and for truncation in the LSB I am getting this quantization noise. Okay. So, then another point is that is which is basically scaling. Okay. So, what is scaling? Scaling basically is needed for finite word length implementation, implies maximum representable numbers. Whenever a signal exceeds this value, this overflow occurs. Digital overflow may lead to polarity reversal, hence it may be very harmful to the circuit or to the hardware design. Avoid overflow through proper signal scaling. scale transfer function may be as C multiplied with the Hz instead of Hz, where Hz is the corresponding transfer function. So, what is the meaning of scaling then? Meaning of scaling means, suppose, okay, let us consider one of the example. At the time it will be much more visible. Suppose I have to do this, suppose I have the number as 2.5. Okay. So, whenever I am having this 2.5 in fixed point, how it will be represented? If I just take the corresponding that numbers, so the number will be represented as 1 0 and here this is 1. I am basically considering this, that okay, this is the point is here, but how we convert one floating point to fixed point? Basically we repeatedly we multiplied with 2. So, that is 5 means this portion is 0. So, I will take that integer portion 5, which is 101. So, here you see the number basically represented as 101, but in actual the point is basically at that time. So, I have just multiplied with 2, that means the corresponding point is here, that virtually I am considering. Okay. So, now suppose I have to multiply this 2.5 along with this 2.5. Okay. So, if I just have to, let us consider 2.5 that will be multiplied with, let us consider 2.5 that is multiplied with 4. So, the result is 10. Okay. But here actually that to represent this 2.5 properly, you remember that to represent this 2.5 properly, if I just only take the integer portion, so at that time it will be 1 0. Okay. So, 1 0 means only 2. So, at that time I will get the result as 8. So, that means 2 will be the error which I will gather for this particular multiplication. But if I do not require or if I do not need this particular error which will be accumulated for truncation of this fractional part. So, I need to hold the original value. Okay. So, that means at that time 2.5 I need the value of 101 and it is multiplied with 4 means I need the results will be 10, okay, which I basically needs. But because of properly holding that this 2.5, I need in the hardware actually I need the data to be represented as 101. So, now 101 that means which is 5, now that will be multiplied with 2 means the value is 20 now. Now, the thing is that to represent this 20, my original value is what? Is 10. That means, if I just let us consider that 4 bit is basically sufficient enough to hold the corresponding values of 10, but in actual what I am doing, the result is 20 I am getting because of the scaling of this. What I am doing here, I am basically use the scale factor as 2 to hold the proper data of 2.5. So, the result is 20, that means that corresponding result I need to hold the, that is instead of 4 bit I need 5 bit here. But how I will get the original values of 10? So, initially what I did, I basically scaled up this value by 1 bit. So, now again I have to scale down to get the proper result, I need to scale down the corresponding value. So, scale down the corresponding value means now I have to divide it by 2. So, here what I did, I have multiplied, initially I have multiplied one of the that value by 2. So, here I have to divide by the same factor, that is I will get the result as 10. That means, here initial my scaling factor is 2 and the same factor here I have divided to get the proper result. So, here you see the original result is 10. So, here also I am getting the proper result which is 10. So, this is the, that means the kind of techniques we used to get. So, that means what? Here accuracy is basically high. That means, I am not losing any error. That means, I am not doing any error while though I am doing the operation. So, this is the scale factor or this is the scaling of the input variables, which basically happens in the arithmetic operation. Okay. So, this is the scaling. Okay. Then this, if you have a two b-bit numbers has to be added, then the result, what I said, the result has to be this b plus 1 bit number. Okay. And for this truncation and rounding or truncation, actually by b bits this quantization noise is basically introduced. Okay. So, in this particular example, I will show you how we can basically get the, that means error, okay, where I will get the error. So, whenever we are dividing by 2, that means I am doing what? So, 100 means, so 20 means 10100. So, divide by 2 means I am just discarding the LSB. So, I am getting the result as 10. If this is not 0, if this value is 1, let us say the result is, so here if it is 3, 3.5 means this is 7. So, 7 means it will be 111. Now, I have to multiply this value with, let us consider 3. So, 7 into 3, the results will be 21, right. So, 21 means the corresponding representation will be, right. So, here if I just discard the LSB, what will be the results? That will be 10, right. But in actual, what will be the results? That is 3.5 multiplied with 3. So, this is 10.5. That means, because of this truncation of this LSB, I am basically gathering the error of 0.5 over here. Okay. But if I just consider at that time something like this, so I will not get it. That means, for if I, while we are doing this scaling up, so at that time if I get whatever operation I am getting, at that time if I am getting the number as odd and then I am doing the truncation, so obviously surely I will accumulate the error. If this is the results is even and then we are doing the LSB, means what? At the 20, if this 0 has been discarded, that means 0 discarded means no, there is no chance of doing any or accumulating any error. As this position is 1, so that means I am accumulating the error. Okay. So, this position 1 means the number is basically even, odd. So, odd number, then doing truncation, obviously you are getting the, that means you are accumulating the quantization noise or the truncation error you are basically doing. Okay. So, this is the example of this scaling. Okay. And now, this quantization that maybe have deterministic nonlinear effect, which may give rise to this limit cycle oscillation. Okay. So, these are the facts. Now, we will consider that what is rounding, what is truncation and what is magnitude truncation. Okay. So, that means here if you just see, suppose rounding means if actually the original value is something like this. Okay. So, that means this may now it may get, or this value that may be get just lower or upper of this, but in truncation always it will be whatever is the original, that means the value, it will be just below 1. What I say, why it is that? Because truncation means what? I am just discarding. Okay. In rounding means we are just getting the nearest value of it. Okay. So, that is why truncation, in truncation it will be always just the below of this particular, that means the particular line. In magnitude truncation, so based on that we can take the decision. So, there is the corresponding that error curve, that is probability of error that may occur within the range. So, in this truncation the error is this. So, magnitude truncation the error may be this. Okay. So, then this quantization noise, what I said that in the previous slide, this quantization effect that may be you can calculate. So, here there is a procedure of doing that, that is this statistical analysis based assumption you can do for this quantization noise analysis. Okay. So, in this statistical analysis based noise analysis, that means this quantization noise analysis, each quantization error is random with uniform probability distribution function. Okay. So, if you just see the previous slides, then a quantization error at the output of a given multiplier are uncorrelated and independent. Quantization error at the output of different multipliers are uncorrelated and independent, and one noise source is intersected for each of the multipliers. Since the filter is linear filter, the output noise generated by each of the noise source is added to the output signal. Okay, means what? Basically, whenever we will calculate the overall transfer function, so at that time each of this basically means what? Actually, the point is that whatever analysis we are doing, so that is based on the overall this quantization of the, considering the fact of quantization in the coefficient as well as quantization in the arithmetic operation, whether that is of multiplier or that is of adder, for both. Okay. So, considering that fact, we are basically getting this particular curve or getting this particular graph. Okay. So, this is the, that means this is the way of doing this. So, that means in fixed point number representation, what are the, that means terms which are associated, that is overflow. If we are discard the MSB, at that time we will get overflow error, that means we will get the magnitude of the that means results in a wrong way. If we discard the LSB, at that time we will get quantization error. Okay. And for that I need to find out what will be the optimum word length, keeping in the mind that the performance and the cost both it would be optimal one. For what word length it is of the maximizing in both the case. So, that is the optimum word length for that. So, while we are doing this floating point to fixed point conversion, at that time we have to keep remember of these things. Okay. So, and more of the analysis we can do in using in MATLAB or not MATLAB, in SPW or in Cocentric. So, these are the tool set where you can analyze your algorithms, what will be the effect for floating point to fixed point conversion. Okay. So, if you need, actually this is not, this is just to give the idea about what is happening and how basically you can calculate. So, there is more on to this. So, that means you have to do a rigorous analysis how you can do. So, whenever you are basically doing your project or you are doing your work, so at that time how you have to do that, there is a method. So, for that you can go for this, the help which is available with this particular tool set, or any material which is really available on the internet, so that you can get. Or else what you can do, if you are more interested how to do that, then please let me know via discussion forum. So, you just you just let me know by asking that, okay, I need to more on this for my purpose, for my project work or for my work purpose. So, any purpose, if you just interested more to, this is just the basic idea, but there is more of, for each of this point there is more. If you want to know more, then please let me know. I will try my level best to help on that particular regards by providing any tutorials or any other documents if I am having it. So, obviously surely I will try to share with you. So, this is for today. Thank you for this today's class.